Okay, this video is going to cover the second half of the 1-4 notes, which covers what extreme values we have in a function and where the function is increasing, decreasing, and constant. When we look at a graph to read it, and we're talking about domain values and range values, we always read the graph from left to right. If the graph is going up as we move from left to right, we say that the graph is increasing. If the graph is going down from left to right, in other words, if the slope of the overall piece is negative, we say that the graph is decreasing. There is one other option, and that is as we move from left to right, the graph does not increase or decrease, in which case we would call that part of the graph a constant section. When we're doing this, when we're discussing increasing, decreasing, and constant behavior of a graph, we are going to give intervals from the domain. Okay, so we're going to give domain values using interval notation. So, let's do some examples. Here is a graph. We're asked to find the intervals on this graph of f of x where the function is increasing, decreasing, or constant. So if we look at this graph for increasing, the graph starts off down here at negative infinity, and it's increasing as we move across until we come to this point. So this section of the graph is considered to be increasing because as we move from left to right, that function is increasing in value. So this function is increasing from negative infinity until we reach x equals negative 3. As for decreasing, the function is decreasing starting at x equals 1 and continuing forever to positive infinity. And in between, we have this section where the graph is neither increasing nor decreasing. Oops, I wrote the constant answer in the wrong part. This actually goes here. Sorry about that. That is the decreasing section. And then finally, we have this constant section from x equals negative 3 to x equals positive 1. Now notice I'm always using rounded brackets here. If I can ever get my pen to work. There we go. Okay, we're not worried about square brackets, rounded brackets. We're just always going to use rounded brackets for these domain intervals because technically at those points it's not increasing or decreasing because it's switching from one to the other or from one to constant. Okay, next example. We're going to have to estimate a little bit here because the exact values are not right where we want them to be. As we've said before in class, if the graph goes all the way to the edge of the graph, you are to assume that that goes forever. So we've got an arrowhead on each end of this graph. It is going to infinity, both x and y. It's going up and out or down and out forever. So, once again, I'm going to try to color code this. We'll start off with the increasing section of the graph. This graph is increasing at two different areas. It's increasing here until it levels off, which happens somewhere around negative 1. We're just going to estimate it at negative 1. So it is increasing from negative infinity to negative 1. And, there's that and symbol, the graph also begins to increase again at about x equals 2. And it continues up forever. So we would say from 2 to positive infinity. Okay, that's written below. Okay? In between those two sections, we have a section where the graph is decreasing from roughly negative 1 until we switch over at positive 2. And in this case, the graph is not constant anywhere. There are no constant sections. So we would put the empty set sign, the null sign, for where the graph is constant, because there is no section of the graph that is constant. Okay, so then we're moving into talking about extrema. Extreme values, maximums and minimums, are what we're talking about when we say extreme values. There are really two different types of extremes. The first type is what's known as a relative extreme, which is a maximum or minimum value for that section of the graph. Okay, a extrema exists anywhere we have a switch from increasing to decreasing. Okay, if it switches from increasing to decreasing, that would be a maximum value. If it switches from decreasing to increasing, that is a minimum value. So there are two of these to note on this graph, and I'm just going to estimate where they are. At x equals approximately 0, we have a relative maximum, because that's the highest point in that part of the graph, but both ends of the graph are higher than that point. So it's not the maximum of the entire graph, it's just that area's maximum. Same thing at roughly x equals 1.5. There we have a relative minimum. Okay? At that point, it's the lowest section of that graph. The graph is switching from decreasing to increasing, but this whole section down here is lower, which means it's not the lowest point in the entire graph. And then we have absolute extremes, which is it's sort of self-explanatory. Absolute means the total, the maximum or minimum point. And not every graph has these. Not every graph has an absolute maximum or an absolute minimum. In fact, this graph has an absolute max up here at x equals -2, but it doesn't have an absolute minimum. Because there is no value lower than -infinity where the graph is headed on the left end. Okay? So we're going to look at some graphs. We're going to estimate the maximum and minimum values, and we're going to classify those maximum and minimum values as either being relative or absolute. So here we go. If we look at this graph here, you'll notice it does not go to the edge, which means we have stopping points at these 2 points. Okay? This indicates that this graph has a total of 5 extreme values, because there are 5 locations where the graph is either as big as it gets or as small as it gets, and where it switches from increasing to decreasing. We have an absolute minimum at x equals -6 and x equals 5. At both of these values, we are as low as the graph can possibly get. We have a relative minimum at the value x equals -1. Right here is a relative minimum for the graph. It switches from decreasing to increasing at that point. We have an absolute max value at x equals -3. Right here is the absolute maximum value of the graph. And we have a relative max at the point x equals 2. So you can see, that's right here, by the way, that's a relative maximum because it's not the biggest value of the whole graph, just that section. You can see that we can have both absolute and relative maximum values without having issues. Okay, it is possible to have both. So now we'll do this next one here in blue. So that was black. Now we'll do blue down here. This graph has 3 max and min values, and we're going to have to estimate with decimals. We have 2 relative minimums. We have one at x equals negative, let's say 2.1. So we have a relative minimum at roughly x equals -2.1 right here. No, I lied. That is not a relative minimum. We have one over there at x equals 2, roughly. That is a relative minimum over there at x equals 2. It is the lowest point in that section of the graph, but it is not the lowest point of the graph. That's the one I started to describe, which is an absolute minimum at the point x equals negative 2.1. Down here, roughly, 2.1 is the lowest point in the entire graph. We also have an absolute maximum, a relative maximum. I really got to stop saying these things wrong. Here at roughly 0.2. We do not have any absolute maximum because this graph goes forever on both ends, indicating that those two endpoints are both higher than our max value, which means we do not have an absolute maximum. Okay, our final example here I will do in red. Okay, again, it's going off in both directions, which means we only have two extreme values. We have a relative minimum at x is about 1.5, negative 1.5, sorry, and we have a relative maximum at x is about positive 1.5. This is a relative minimum. This is a relative maximum. Neither one of those values are an absolute because the ends are going up and down respectively, meaning that the graph does exist further up and down. Thank you for your time.